Welcome to part 5 on Intro to Angles. In this video, we're going to look at circular motion. Suppose you and your friend are running in a circular track. You are in the inside and your friend is on the outside circle. If you both start at the same time and finish at the same time, who is running faster? Why is this the case? So you may be saying to yourself, well, obviously the person on the outside circle is running faster than the person on the inside circle, which would be true. But why is that true? Well, if you are maintaining the same pace, that means that the angle that you are going through is staying the same. Now, how fast you're going, that's a different story. But the fact that you're both maintaining the same angle says that the person on the outside has to work harder to keep up. So there are two ways to describe the rate of motion for a point moving around a circle. Linear speed is the rate of change in distance over time. So that would just be keeping track of how much distance they've traveled circumference-wise with respect to time. Angular speed is the rate of change in the central angle. So this is how you keep track of the fact that they're both keeping pace with each other, regardless of the fact that the person on the outside circle is moving way faster to keep up with the angle changing. Suppose a point moves along a circle of radius r, and the ray from the center of the circle to the point traverses theta radians in time t. Let s equal r theta. Well, this is something we've seen before, because this is the arc length. So the distance the point travels in time t is this, s equals r theta. Then the speed of a point can be defined in two different ways. There's a linear speed, v, velocity, equals s over t, and angular speed, and this is another Greek letter, omega equals theta divided by t. So the next question is, can you come up with the relationship that shows that proportion? This might not be super obvious, but we can use a substitution of one of these formulas into the other and get v equals r omega. Let's see if we can do some substitutions. If v equals s over t, and we know that t in the omega equals theta over t, we could say t times omega, multiplying both sides by t, equals theta. Therefore, if I wanted to solve for t, I would divide both sides by omega. And so substituting t in to v equals s over t, we will have v equals s over theta over omega, and this will give us s times omega over theta. So if I were to substitute s with what I know s equals r theta. So I'm going to replace the s with r theta multiplied to omega divided by theta. And that will allow me to reduce out the thetas. And I get exactly what I'm supposed to. This is how the relationship works. It's not super intuitive, maybe, when you first look at it, but that's how it works. So suppose a point moves one revolution around the circle of radius r in 1 minute. What is its linear speed? So I know that the linear speed is how far it's gone in 1 minute. and s equals r theta over t, then I can replace the theta with 2 pi. And I know that because it says 1 revolution around the circle. So that means 2 pi in radians. So replacing the theta with 2 pi, I'll have 2 pi r divided by time, which is 1 minute. Angular speed is looking at how fast the angle is changing. It is not so much worried about how far you're going around the circle with respect to time. It's how fast the angle is changing from the center. So how fast is it going around and around and around and around and around? Hopefully that makes sense. So let's look at that formula. Omega is equal to theta over t. Now, theta is the angle that it's going through or moving through, and time is how long it takes to move that angle. So notice that in this case, we don't care about the radius because the radius will change how far, the distance. But again, we're not worried about that. All we're caring about right now is how the angle is changing. So this will just be 2 pi per 1 minute.